All right. Hey guys, Aaron Cooner here with AccuFoam. Talked to Ben Mons this morning, and he had a lot of questions on tuning foam, and asked me if I could type something up or make a short video on why and how we tune foam the way we do. He's been a big one on wanting an application guide, and I'm very hesitant to put out application guides, and here's why. There's too many variables that play in effect. And to explain this to you guys, I'm going to just try to do that in this short little clip here. An application guide is a handy tool. It's not a great thing when it's a new sprayer. I sprayed for almost 21 years, and I never looked at an application guide for any manufacturer's material. I stabbed the kit, I read the foam, and I did what the foam needed me to do. So I'm going to try to kind of explain why we do what we do and some of the factors that play in effect with that. And hopefully I do a decent job. I'm sure I'll butcher it. So this is Foam Training 101. So when I am working with a client and the guy is spraying a certain way, it really dictates what we do and why we do it. And also the equipment plays a large part in that as well. If he has a relatively small machine with a small delta T, the delta T would be the machine's ability to take the material from the temperature it comes into the machine and what it can actually raise it to. A E20, for instance, may have a 40 to 50 degree delta T. H40 may have 90 degrees of delta T. And there's a lot of factors that play into that as well. You have to make sure that the equipment is sized appropriately with the mixing chamber they're using, etc. If I throw a 52 in a E20, I'm going to severely affect the machine's ability to keep up. It has a relatively small capacity heater box. It has a horseshoe heater. They're not near as efficient as like a hydraulic machine with a long rod heater. It has a large capacity hopper, so it has more dwell time. It's going to be able to apply way more heat and attain more material, and it has more time to heat that material up. If I throw a large chamber in a small machine, I'm going to literally outrun that machine's ability to heat that foam up. So no matter what I put on that digital display, doesn't mean that's what I'm getting at the gun. So there's a lot of factors in here, but I want to get through the basics. Another thing that can play effect is hose length, environmentals. There's so many things that happen day to day. Just because I was tuning the foam at this temperature this day doesn't mean it'll work tomorrow, and it could be relatively same ambient temperatures outside. It could be a different substrate. It could be a different environmental anomaly. So I want to go over a few things with you guys. Hopefully this will help, and God willing, I hope this is my last take, because I thought this would be easy, and I think I'm on like 10th one. So some of the forces imposed on why we tune the way we do. I want to talk about just a basic fluid dynamics. If a material had zero viscosity, you would get a linear flow through a hose, which means all the material in that hose from wall to wall would flow at the same rate. Once you add viscosity, you get what's called a turbulent flow, which means the material on the outer edges of the hose is basically sitting there stationary, and the material actually passing through the hose is basically passing through the center of the hose. And when this happens, when material runs across material, there's a term we use, it's called shear stress. The shear stress is the friction of material moving across material. ISO actually has a way lower shear stress rating. It's a little more viscous. It flows across itself way more efficiently than the resins. And this is going to play an effect on how we tune the way we do. With that being said, centipoise is the term we use for the measurement of viscosity. You'll hear that a lot in this industry. If you haven't already, I'm sure you will. And I want to move on to the Bernoulli's principle. So anytime we reduce the diameter of a hose, at that choke point, what will happen is that material going through that choke point, such as like the block on a gun, and in the gun there's actually probably 2 or 3 places where we actually reduce the size of the orifice. What's going to happen is that material is going to speed up. And when it speeds up, it actually loses temperature, and it also creates vortices, which vortices can actually result in more friction on the material itself as well. This is why having warm foam is so important. Whenever we talk about, in the wintertime, you'll hear the first thing I'll ask, to the point where it's almost humorous. I take so many phone calls in the winter, and people are saying I'm blowing off ratio foam. I took my at the time, 10-year-old daughter on a service call when I first started here. She was homesick, and she ran with me on call. I was just gonna be on call at home. We ended up having to get called out at site. When we showed up, they were telling me what's going on, and my daughter asked the contractor, "What are your drum temps?" She's heard that term a lot. So whenever we're talking about the centipoise of a material, when we QC out our resins, we do it at 77 degrees. Our closed cell, for instance, runs 550 to 600 centipoise, and the ISO is sitting there at 300 to 350, depending on which one it is. If you look at the viscosity curve on the ISO, it's relatively linear. At 60 degrees, it's not much difference than it is at 80 degrees. It's a very gradual climb. On a resin, however, at 77 degrees, we're at 550 centipoise. At 60 degrees, we may be 1,000, 1,200 centipoise. So it's an exponential climb, and that's why it's so crucial, if we're gonna make good foam, that we keep the material warm. We can't stress that enough to our vendors and our sprayers. That's the first thing I'm gonna ask you when you call me and tell me that materials, running off ratio. I'm gonna ask you what your drum temps are, especially in the wintertime. This varies a little bit between open and closed cell. Open cells, resins run relatively lower centipoise than the closed cell, so it's a little easier to mess with in that respect. With closed cell foam, most of the reaction is done chemically. We have blowing agents and catalysts, and we actually, we create that reaction with chemicals. It's something we program into the foam. With open cell, it's more or less done with heat. That's generally why we process our open cell way hotter than we would our closed cell. Moving on, whenever we're talking about the pattern on a gun, if we have a relatively narrow pattern, that would indicate that the foam's a little too cold and we're not getting that pattern to fan out. So obviously I would recommend bumping in more heat. We want that pattern to spread out. When I'm setting pressures, that's all gonna be kinda based on what they're spraying and how they're spraying. If I've got a contractor in between a 2x6 wall and 16-inch center, and they're standing relatively close, let's say, within a foot of the substrate, I'll run a lower pressure and a higher temp. What I'm wanting to do is I want that foam to hit as a liquid, atomize on the wall, and then grow out. If you stand back 4 foot at a low pressure, what could happen is, from the time that foam leaves that gun, it's decelerating all the way to the wall. The last thing we want it to do is start reacting off on the way to the substrate. That can actually result in a bunch of little foam-looking BBs that hit the wall, kind of melt together. It can affect dimensional stability and other things. So when I'm setting my pressures, it's based on how the sprayer's spraying or what they're spraying. And me, myself, like when I was up in a 16-inch cavity, I would run substantially lower than if I was on a red iron building where I'm standing back 3 to 4 feet. So that plays an effect. Also, the temperatures will gradually vary too. If I'm standing way off, I'll run a higher pressure and a lower temperature on my heat setting sometimes, because again, I want that material to hit as a liquid, react off, bleed together, and make a nice looking cell structure. We don't want a lot of pinholing, etc. And ultimately, we're trying to get the AccuButter, so that's kind of what this entails. So on your machine, if you're running a small Delta T machine, you're running the correct mixing chamber versus a long rod heater with a lot of dwell time and with a lot of hose, that's going to affect how we tune, etc. If I was trying to achieve 500 PSI at my block, if I had 50 foot of hose, I may only need to set that machine at 700 PSI dynamic pressure. The difference in dynamic and static pressure are, like, if I was sitting here at 1,015 at rest, that would be my static pressure. When I pull the trigger, these tend to drop off 100 to 200 pounds. Whatever it drops to would be my dynamic pressure. So whenever we're talking to a sprayer, we'll ask him, what is your dynamic pressure? That's what it's dropping to, because when he's pulling the trigger, that's actually what he's achieving. So if I had 50 foot of hose, again, trying to achieve 500 to the block, it may take 700 PSI. If I had 300 foot of hose, it may take 1,400 PSI to achieve 500 at this block, because of the shear stress imposed on the hose. By it being longer, there's more friction, so it's gonna take a greater pressure. Whenever you're spraying foam, one of the big things is off ratio. Me and Brent have gone back and forth on this. And after hours of YouTube videos and studying fluid dynamics, I kind of figured out what's going on when a machine's working properly and there's no pump slippage, the packings are correct, everything's working properly. If you were to cross over a gun or blow off ratio foam, there's a phenomenon happening there. Let's say this is kind of a diagram I drew out for that. So like, let's say that our ISOs, when like dynamic pressure would be 1,000, our resin's at 1,500. What can happen is, as the material's entering the mixing chamber, we've got 1,000 here, 1,500 here. The ISO being thinner viscosity is leaving out a nozzle fairly unrestricted, where the B has a lot of back pressure. It's harder to move through that hose. It'll actually build up pressure. It can start to cross over into this impingement port on the ISO side. When it does that, this ISO will build up enough pressure. If you're lucky, it will force its way back out and out the nozzle. So I call this zebra striping. You'll see a weird phenomenon happening where you'll get kind of a darker patch of foam or a lighter patch of foam, and darker and lighter. And it's pretty obvious that we're getting less of one component than the other at times, but it's close enough in pressure where it's kind of battling back. But what's happening is there's a tug of war going on inside this mixing chamber, and what I would call off ratio, Brent would refer to as bad mixing. Now, if you go far enough off ratio, eventually this will go ahead and cross over into this impingement port, go down in the gun. There's a check ball assembly that's made to catch it, but let's say those pressures are fairly constant and that ball doesn't seat down because the pressure divide is not that great. It can cross over into your whip, into your hose. We could be talking about $3,000 to $5,000 worst case scenario. You know, it could cost some money. So it's crucial that we're blowing on ratio, mixing our foam well at the nozzle. This is going to kind of determine how I plug in my tune. Your older machines are like your PMCs, the not as, you know, if a machine's not running in resistance mode, they'll have a thermocouple. That thermocouple usually sits in your ISO line. So a lot of times what I like to do is I like to set my A heater and my hose heat at the same temperature, because ultimately I want when I pick up that gun and I start shooting, I want to spray the same as after it's been sitting for a while, or if I'm ramming on that trigger and just dumping kit after kit, I want it to react off the same the whole time. So in order to do that, what I like to do is I like to offset my temperatures. So I may run my B side 6 to 8 degrees higher than my A side. What that's doing is it's reducing that viscosity. It's giving us more so of a linear flow. And ultimately, we're wanting to reduce those viscosities to where it's coming in the mixing chamber, meeting in the middle, and propelling out the nozzle at the same rate. If you're ideally with closed cell, you know, they're within 200 or 300 pounds of one another. Again, that machine's pumping 1 to 1 if it's working properly every stroke. But if these pressures get too high on the B side, what that's simulating is it's taking 500 pounds more pressure to achieve the same flow rate out of that block and gun as the ISO side. So essentially it's taking a lot more pressure to move that material. When those pressures get too offset, you can cross over, you can make for bad mixing, etc. So by increasing the temperatures on the B side, I might bring that down from 1,000 to 15 down to like 12, 1,300. That's kind of where I'm comfortable with. And the other thing is, especially in closed cell, there's a blowing agent that's trying to boil after 83 degrees. And there's some other phenomena that happen that can actually raise that line pressure. But the biggest thing is shear stress and the amount of pressure it's taking to move that material through the hose. So by increasing temperatures, we can reduce the mass stress on that line, and we can kind of get those running more equally. If a guy's having trouble with drill at times, there's a lot of different factors that can play in effect. One would be humidity, one could be whether their air dryers are working correctly. A lot of guys run refrigerated air dryers. Those depend on the ability to cool the air running through that system, which drops the dew point, which allows the water to separate from the air. If you have an air dryer sitting right over top of a generator, it may not be working properly. You may not be getting rid of all that moisture that's going through that system. And then what can happen is ISO reacts off with moisture. So if there's a little residual ISO in this mixing chamber, and then every time you let off the trigger, it's using air to clean out that passage. If it's moist air, it's gonna go ahead and set up that ISO. It's gonna foul that chamber. It's gonna be a nightmare. So that would be a big one, would be moisture related. The other thing is sometimes if you get your temperatures too hot, you can actually start setting up foam in the nozzle, which would also lead to more draw out times. Ideally, we want to get to like 20, 30-minute draw out times. Now, if you were to set that gun down, you're moving room to room. When I was spraying, I automatically assumed if that gun had set for any amount of time at all, I probably needed to drill it out. Because if there's any residual in that mixing chamber and there's been air sitting there blowing through it, it could set up whatever's left over. It could have a little cleaner in there, it might need drilled out. That's pretty commonplace. If I'm on a big building and I'm just holding on that trigger, my drill out times are gonna be far less than if I'm starting and stopping a lot. And you see this a lot with new sprayers where they're wearing out, they're just taxed, they're cashed. They'll do a lot of start and stop and they'll find every reason to stop, go get a drink, whatever. Their drill out times are gonna be far greater than a guy that can just stand on that trigger and keep stuff done. So when we're tuning foam, we have to think about heat settings, distance, and pressure. If the face of the foam is not to our liking, if it's real jaggy, rigid, more than likely what's happening is its tack time is a little slow. When we're blowing, especially big lifts, and you're going in a 16-inch center cavity, going side to side, you're basically distorting the foam that you already put down. So one way we can fix that is we could pump a little bit more heat in it, try to get that tack time in. We want that foam to firm up fairly quickly, so when we're blowing into it, we're not distorting it, pushing waves and making it ugly. The other thing we can do is we can reduce our pressure, which actually, because of the Bernoulli principle, then the faster you move it through a passage, you're actually losing more heat. And if you have a questionable machine as far as delta T or the material's a little cold, more dwell time lets the foam heat up a little bit more, it helps stay more constant. And by reducing pressure, we're losing less in these pinch points. When it knucks down, we're losing less temperature as well. So if it's jagged, nasty looking, we can bump our heat up a little bit. If we get to the point where our drill out time starts to increase, then we can bump that heat back down a little bit, reduce the pressure a little bit. And again, that's where the pressure settings differ greatly because of the amount of line they're using, etc., the amount of shear stress that's on that. You really just kind of, after a while, you'll start to see it, feel it, hear it, and you kind of know what you're looking for and you adjust accordingly. And that takes time, but ultimately we're trying to get to AccuButter, and that's our goal. So with that being said, I hope this helped y'all kind of get a little bit of a grip for it. There's far more that goes into it, and this is pretty elementary, but hopefully that gives you a better understanding as far as what's going on and how we tune the way we tune. Thank you all.